Let us continue alkali metals. In the alkali metals, we have seen that alkali metals are soft. For example, sodium can be cut with a knife. Therefore, we can say alkali metals are soft. We can say down the group, what happens to the softness? That we'll see. Down the group, size of atom increases. Therefore, softness increases. Down the group, softness increases. Okay. Now, how the melting point will be there down the group, we will see. Now, we'll take lithium. Lithium melting point is 454 Kelvin. Sodium melting point is 371 Kelvin. Then potassium. Potassium melting point 336 Kelvin. Rubidium 312 Kelvin. Cesium 302 Kelvin. Cesium 302 Kelvin. Now, the melting points of alkali metals are very low because they are soft. So down the group, size of atom increases, therefore softness increases, therefore melting point decreases. The melting point of cesium, if we see 302, 302 in the sense degree Celsius, if we see 29 degrees Celsius. Degree Celsius, if we take 29 degrees Celsius, therefore cesium will exist as a liquid. If you give temperature more than 29 degrees Celsius, it will exist as a liquid. Okay, so melting point is like this. How the boiling point will be there, that we'll see. How the boiling point of alkali metals will be there. Boiling point of lithium is 1615 Kelvin. Sodium 1156. Potassium 1032. 1032. Rubidium 961. Then cesium 944. Cesium 944. So down the group, boiling point decreases because softness increases. Okay. Then we will see ionization energy. Down the group, size increases. Therefore, distance between nucleus and outermost electron increases. So attraction decreases. Therefore, removing electron becoming easy. Therefore, energy required to remove electron decreases. Therefore, how the first ionization energy will be there, that we'll see. First ionization energy for lithium is 520 kilojoule per mole. 520 kilojoule per mole. Then sodium 496. Potassium 419. Potassium 419. Rubidium 403. Cesium 376. Cesium. So first ionization energy decreases down the group. First ionization energy decreases down the group, we can say. Sorry. Next, we'll see alkali metals color. Alkali metals are a silvery white. It is white color like silver. How silver ornament color will be there, like that it is appearing. It is soft and light metals, we can say. Then we will see hydration of alkali metal ions. Hydration we'll see. Now we will go for a hydration. Now lithium we will take, we will convert this into Li plus. Li plus configuration is what means helium configuration. This second shell is completely vacant. Second shell is completely vacant. Now this 2s 2p, totally 4 orbitals. That means 2s contains 1 orbital, 2p contains 3 orbitals, totally 4 orbitals intermixing with each other to give 4 hybrid orbitals. 4 hybrid orbitals. These hybrid orbitals are called sp3. sp3 hybrid orbitals, you can see. So this Li plus is having 4 sp3 vacant hybrid orbitals. Okay. Now this Li plus is providing 4 vacant sp3 hybrid orbitals like this. 4 vacant sp3 hybrid orbitals in this way. Now water molecule comes. Water molecule is having lone pairs. Water molecule is having lone pair. Now between this vacant orbital and this lone pair, dative bond is possible. Dative bond is possible. So lithium gets 4 dative bonds with 4 water molecules. 4 dative bonds with 4 water molecules like this. 4 water molecules like this. This is called a primary shell. This we can call as a primary shell. In the hydration, the first step is formation of primary shell. Next step, water molecule comes. It forms hydrogen bond with this water molecule. Hydrogen bond. So this forms a second shell. This is a second shell. Now this forms a second shell, we can say. Lithium ion Li plus, this Li plus, primary shell, secondary shell, all together called hydrated lithium ion. Hydrated lithium ion. Hydrated lithium ion. We can represent this as Li plus Aq. Li plus Aq we can represent. This process is called hydration. So hydration means Li plus gas you have to take, that you have to convert into Li plus aqueous. In this process, what is the amount of heat involved? That is called enthalpy of hydration. That we can call it as enthalpy of hydration, we can say. Enthalpy of hydration. This enthalpy of hydration means here we are taking Li plus gas. It is forming primary shell. That means in the primary shell, coordinate bonds are there. Then secondary shell is producing. There hydrogen bond is producing. In the formation of primary shell, dative bond is producing. In the formation of secondary shell, hydrogen bond is producing. So due to formation of bond in this process, heat will be liberated. Therefore, it is exothermic, we can say. Now, hydration enthalpy of Li plus gas is 506 kilojoule per mole. Kilojoule per mole in the sense 1 mole of Li plus ions undergoing hydration. That energy involved is called hydration enthalpy. So hydration enthalpy means 1 mole of Li plus ions undergoing hydration, while involvement of energy, how much energy is involved, that is called hydration enthalpy, we can say. Now next we will take sodium, we will take Na plus gas, we will take Na plus gas. This electronic configuration is neon. This valence shell 3s is containing 0, 3p contains 0, 3d contains 0. Now one 3s orbital, 3p orbitals, 2d orbitals, 2 3d orbitals intermix to give 6 hybrid orbitals. Those hybrid orbitals called sp3d2 hybrid orbitals. sp3d2 hybrid orbitals. Now water provides a lone pair. Water provides a lone pair. This lone pair present in sp3 orbital. Now between this water oxygen lone pair sp3 orbital and a vacant sp3d2 orbital of Na plus, dative bond is possible. So like this, how many dative bonds possible? In the sense 6 dative bonds possible. Around Na plus 6 dative bonds possible. So 6 water molecules making dative bonds with Na plus gas. Na plus gas. This is called primary shell. This is called primary shell. Then secondary shell. In the secondary shell, the water molecule is there like this. It makes a hydrogen bond with this hydrogen. This forms a secondary shell. This forms a secondary shell, we can say. Now Na plus primary shell, secondary shell, all together is called hydrated sodium ion. That is represented as Na plus gas, Na plus aqueous. So now we will see hydration of sodium. Hydration of sodium means take Na plus gas. It takes water molecules and becomes Na plus aqueous. This process is called hydration. The energy involved in this process is called hydration enthalpy. So hydration enthalpy of sodium is how much means minus 406. Minus means exothermic. So we have seen hydration enthalpy of sodium we have given here. In the previous case we have given lithium. Now we have given sodium. For lithium, what is the hydration enthalpy? For lithium hydration enthalpy we will see 506. For sodium 406. That means how much difference? 100. 100 kilojoule is different. Why for lithium hydration enthalpy is more? For sodium hydration enthalpy is less. Because lithium size is small. Li plus size small. Li plus size small. Na plus size high. Therefore, in the primary shell, dative bond is possible, coordinate covalent bond is possible. That strength is high. Here, dative bond is possible. That strength is low. Then, distance between nucleus and water molecule is less. Here more. Therefore, in the secondary shell, large amount. Now, so Li plus and Na plus in the secondary shell, if you see, large amount of water molecules will be there for lithium. Less amount of water molecules will be there for sodium. Therefore, Li plus goes for higher extent of hydration. Therefore, extent of hydration will be high for Li plus than for Na plus. Therefore, we can say extent of hydration is high for Li plus than for Na plus. For Na plus, extent of hydration is less. Therefore, hydration enthalpy is high for Li plus, less for Na plus. Hydration enthalpy is less for Na plus. For Li plus, hydration enthalpy is more. For Na plus, hydration enthalpy is less. What is the magnitude of hydration enthalpy for Li plus in the sense that is 506 kilojoule, for Na plus minus 406 kilojoule. For Li plus 506 kilojoule of energy is liberated for 1 mole. For Na plus 406 kilojoule is liberated for 1 mole. Sir, down the group size increases. Therefore, what will happen to the hydration enthalpy? Hydration enthalpy decreases. So, for lithium, hydration enthalpy is minus 506 kilojoule per mole. For sodium, hydration enthalpy is minus 406. For potassium, hydration enthalpy is minus 330. Rubidium, for rubidium, hydration enthalpy is minus 310. For cesium, hydration enthalpy is minus 276. So down the group, size of alkali metal increases. Therefore, extent of hydration decreases. So hydration enthalpy decreases down the group. Next, we will see flame coloration. Next, we are going for flame coloration. So, this flame coloration, how to do this flame coloration, we'll see. Now we will take a alkali metal sodium. This alkali metal sodium, we have to take under flame coloration. So we will take this alkali metal in the form of a salt. So sodium in the form of sodium salt. Sodium salt in the sense, which salt we will take? Sodium chloride, sodium sulfate, sodium nitrate, sodium phosphate. Like this, many salts are there, sodium salts. Any one of the salt you take. Then add corn HCl into the salt. Make it as a paste. Make the salt as a paste. This paste you take in the one end of the glass rod. So we are taking the glass rod. In one end of the glass rod, we are taking the paste. This paste is introduced into the oxidizing flame of the Bunsen flame. Oxidizing flame we will see. Now the flame, if you see in the Bunsen flame, the two flames will be there like this. One is inner flame, another one is outer flame. Now we will say this is outer flame. This outer flame is called a oxidizing flame. This inner flame is called a reducing flame. This inner flame is called a reducing flame. This outer flame is called the oxidizing flame. Introduce this paste into this outer flame, which is called oxidizing flame. This paste we have to introduce into this oxidizing flame. What is the color of this flame? This flame color is flame is blue color. Now this paste we are introducing into this outer flame, oxidizing flame. The flame becomes the flame color becomes golden yellow. The flame color becomes what in the sense? Golden yellow. Why is it so? Now sodium salt contains Na plus ion. Sodium salt contains Na plus. This sodium salt is pasted with, mixed with con HCl, therefore it becomes sodium chloride. In this paste, sodium chloride is present. This sodium chloride contains Na plus. This Na plus takes electron from flame. This Na plus takes electron from the flame, then becomes Na. So now the configuration is neon 3s1. This 3s1 electron goes for excitation. Due to excitation, it absorbs some amount of some wavelength. Rest of the wavelength is emitted. Therefore, this flame is appearing golden yellow. So sodium will appear what color in the sense? Golden yellow in the flame. Sodium appearance normal condition is silvery white. In the flame, it is appearing what means golden yellow, we can say. Sir, why we have to make the paste as sodium chloride? Why we have to make the paste as chloride salt? Because we added con HCl. We are adding con HCl means we are making the salt into chloride salt. Why to make the salt into chloride salt? Because that is having high volatility. Highly volatile. Chloride salt is highly volatile. This chloride salt is highly volatile, easily evaporating here. If it is highly volatile, so easily evaporating, therefore we can see the flame coloration. Flame coloration in the sense the introduced one should be highly volatile, then only we can go for flame coloration. So we have to go for flame coloration by introducing the paste of chloride salt because it is highly volatile. So in order to get chloride salt, the given salt is made as a paste with con HCl. Okay. Next, we'll take lithium salt. We'll take. Similarly, convert lithium salt into lithium chloride by mixing with the con HCl. That lithium chloride introduced into the flame, oxidizing flame. What will happen means lithium chloride contains Li plus. With the flame, it becomes LiOH. With the flame, it becomes LiOH. That means it is combining with the water molecules and becomes LiOH. This LiOH is giving what color to the flame in the sense crimson red. It is giving crimson red. Crimson red in the sense deep red color. Crimson red means deep red color, we can say. So in the flame coloration, lithium gives what color? Crimson red. Lithium gives a crimson red color, we can say. Lithium gives crimson red. This crimson red is having what wavelength? 670.8 nanometer. Next, sodium gives a golden yellow. This is having what wavelength means? This has wavelength 589.2 nanometer. Next, potassium gives violet color to the flame. This has wavelength 766.5. Rubidium gives red violet. Rubidium gives red violet. This wavelength is 780. 780. Cesium gives a blue color to the flame. This wavelength is 455.5 nanometer. That means this lithium salt is emitting crimson red. That wavelength is this much. That means it has absorbed. It is emitting red color. It is emitting yellow color. It is emitting violet color. That means down the group you see, down the group, emitted wavelength increases. Therefore, absorbed wavelength decreases. So, it is high wavelength emitted means low wavelength absorbed. That means high energy absorbed for the excitation. Why it is absorbing high energy for excitation? Because small size. Therefore, down the group size increases. Therefore, absorbed energy decreases. Energy absorbed quantum that decreases. So wavelength absorbed decreases. Next, wavelength emitted increases. So the color is like this. Next, we will see reducing power. Next, we are going for reducing power of alkali metals. Reducing power in the sense reducing nature. That means acting as a reducing agent itself undergoes oxidation. That is the mean. Now we will see reducing power of lithium. We will take lithium, that is solid. We will convert this lithium solid into lithium gas. Then we will convert this into Li plus gas. Then we will convert this into Li plus aqueous. That means when lithium acts as a reducing agent, it will go for so and so process, and finally it will become like this. For the entire process, you find a delta H. Then you find a delta S. Then you take the temperature, given temperature you take. Then you find a delta G. From delta G, we will find a E naught. That E naught value, how much means? We are finding a E naught. Now we will find a E naught for this. E naught is how much in the sense 3.04 volt. 3.04 volt. Now, E naught means standard potential. E means potential. Potential in the sense tendency to undergo like this. Tendency to undergo like this is a 3.04 volt. Next we will take sodium. In the same way, we are converting sodium into Na plus gas, Na plus aqueous. That means sodium solid we will take. That sodium solid we are converting into sodium gas. Then Na plus gas, then Na plus aqueous. For this we will see E naught. E naught is how much means 2.714 volt. So now you see which is having higher potential to convert like this? Lithium. That means lithium is having higher tendency to go for like this process than sodium. Therefore, lithium donates electron with higher tendency than sodium. That means don't see only ionization energy. Reducing nature means it has to give electron to another species. It is giving means it is becoming what? That we have to see. It is becoming like this. Therefore, we have to see which energies and all. We have to see sublimation energy. That means if it is going for sublimation, okay. Otherwise, we have to see melting point and boiling point. Both we have to see. If it is not going for sublimation, then we have to convert solid into liquid, then liquid into gas. Therefore, melting point, that energy, boiling point, that energy. So this is endothermic. It is ionization, endothermic. It is hydration, exothermic. We have to see overall process energy, we have to see. Overall delta H, we have to see. Overall delta S, we have to see. Then only we have to come for conclusion. Okay. Therefore, this overall process says that lithium has higher tendency to donate electron than sodium. Lithium has higher reducing nature than sodium. So lithium is a better reducing agent than sodium. So reducing nature, we said like this. Then we will take potassium. We will see for potassium. For potassium, K becomes K plus aqueous. E naught value is 2.925. Now, with sodium and potassium, if you see, potassium has higher reducing nature than sodium. So for potassium, reducing nature is more when compared to what in the sense sodium we said. Next, we will take rubidium. Rubidium solid we will take. For rubidium, we will see Rb plus aqueous. Here E naught value we will see for rubidium. For rubidium, E naught value is 2.93 volt. 2.93 volt. Then we will take cesium. Cesium, if you see, the E naught value is how much in the sense 2.927. 2.927 volt. E naught value for cesium. So we can say that potassium reducing nature is more than sodium. Rubidium reducing nature is more than potassium. Cesium reducing nature is nearly equal to rubidium. Even rubidium and cesium also difference is not much. The rubidium and potassium also the difference is not much. But sodium and potassium difference is there. Sodium and potassium difference is there. Potassium, rubidium, cesium difference is not there. Little difference, very little difference. Very little difference is there. Potassium, rubidium and cesium. Sorry, okay, anyhow. Now, from sodium to cesium, what happens to reducing nature? That we'll see. Reducing nature increases. From sodium to cesium, if you see, reducing nature increases, we can say. So, from sodium to cesium, we are taking reducing nature. Sodium to cesium, reducing nature, what happens means reducing nature increases. Therefore, the weakest reducing agent is sodium. Weakest reductant is sodium, we can say. Strongest reductant, lithium, we can say. Strongest reductant, lithium, we can say. Now, lithium shows exceptional behavior or not, you see. Sodium is weakest reductant, lithium is strongest reductant, down the group reducing nature increases. That means lithium shows exceptional case, no? Actually, if you see, converting solid into gas is endothermic. Where that energy highly required, do you know? Lithium only. This is ionization energy. It is endothermic. Where this energy highly required means lithium only. Hydration is exothermic. Where this exothermic nature is more, no? For lithium. Here exothermic nature is more. Though these two endothermic natures are highly dominant for lithium when compared to other alkali metals, hydration enthalpy overcomes that effect. Hydration enthalpy is more for lithium. than for others. This we said hydration enthalpy minus 506. Here we said minus 406. Difference is how much? 100. Therefore, because of high hydration enthalpy, the high hydration enthalpy of lithium, it has higher hydration, it has a higher reducing nature. So lithium is acting as strongest reducing agent among the alkali metals. So it is coming as an exceptional case. So among the alkali metals, strongest reducing agent is lithium, weakest reducing agent is sodium. That we can say from E0 values. Okay. Next, we will see occurrence of these alkali metals in the lithosphere. We can see occurrence of alkali metals in the lithosphere. Occurrence of alkali metals in the lithosphere. We are seeing, we are taking lithium. Lithium, how much available in the sense 18 ppm, 18 parts per million. Sodium availability is 2.27% by weight. Weight percentage. Potassium weight percentage is 1.84%. 1.84%. Weight percentage is this much. Rubidium 12 to 78 parts per million. 12 to 78 parts per million. Cesium 2 to 6 parts per million. 2 to 6 parts per million. Cesium 2 to 6 ppm. 2 to 6 parts per million, we can say cesium. So this is in lithosphere. In lithosphere, alkali metals availability is like this. In lithosphere, alkali metals availability is so and so, we can say. Next, reaction with the air, we will see. Next, we are seeing reaction with the air. How alkali metals behave in air, we will see. Alkali metals we will expose to dry air. We are taking alkali metal, we are exposing this alkali metal to dry air. What will happen in the sense? Over the alkali metal, this alkali metal will become oxide. When exposed to dry air, it is reacting with oxygen and become alkali metal oxide. Then with moisture, what it will become means, it will become hydroxide. It will become hydroxide. This alkali metal with the dry air becomes oxide. Therefore, this alkali metal tarnish in the presence of air. It is a silvery white. Alkali metal is silvery white. When exposed to dry air, it is tarnishing because of formation of oxide. In the presence of moisture, the oxide becomes hydroxide. Okay. Next, we'll take alkali metal. This alkali metal is heated with air. Alkali metal is heated with air. Here we will take excess. Here we will take excess. We are taking alkali metal. This alkali metal is exposed to air. Here we are taking excess and it is heated. So what will happen? Alkali metal is heated with excess of air. So what we will get? Lithium forms monoxide mainly. Lithium forms monoxide mainly and little peroxide. Lithium forms peroxide little. Little peroxide it forms. Sodium forms mainly sodium peroxide. Sodium forms mainly sodium peroxide and a little superoxide. And a little superoxide. Sodium forms superoxide little. Whereas potassium, rubidium, cesium forms mainly superoxide. Potassium, rubidium, cesium forms mainly superoxide. They are forming mainly superoxide. Lithium forms mainly monoxide, little peroxide. Sodium forms mainly peroxide and little superoxide. Potassium, rubidium and cesium forms mainly superoxide, we can say. Mainly superoxide, we can say. Why? Why they are forming like this differently? Sir, now we will take oxide. Monoxide we will take. The monoxide formula is O2 minus. Then we will take peroxide. Peroxide formula is O2 2 minus. Then we will take superoxide. Superoxide formula is O2 minus. So this oxide formula O2 minus, peroxide formula O2 minus, superoxide formula O2 minus. Now lithium forms this monoxide. Lithium forms oxide mainly because lithium ion is able to overlap with this oxide electron cloud properly. Sodium forms peroxide mainly because sodium ion overlapping with peroxide electron cloud properly. That means sodium ion size and peroxide size is such that they are making a stable compound. Lithium size such that, oxide size such that they are forming stable compound. Then potassium, rubidium, cesium size such that they are able to be stable with the superoxide. Therefore, size is high means superoxide is stable. Size is high means superoxide is stable. So remember that potassium, rubidium, cesium mainly forms a superoxide. Lithium forms a monoxide. Sodium forms a peroxide. Sodium forms peroxide like this. Set. Now we will take a alkali metal monoxides. We will take alkali metal monoxides. We are taking. This we said with respect to heating alkali metal with excess of air. Sir. Now we will take monoxides of alkali metals. What is their behavior, that we will see. We will take lithium monoxide Li2, sodium monoxide Na2, potassium monoxide K2O, rubidium monoxide Rb2, cesium monoxide CS2. So we have taken monoxides. These monoxides, if you dissolve in water, you will get lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. Like this, they will convert into metal hydroxides. Alkali metal monoxides on dissolving in water becomes alkali metal hydroxides. These are strong bases. Therefore, these oxides are having strongly basic strength. These oxides are strongly basic because these are strong bases. Okay. So alkali metal oxides we can say strong bases. Alkali metal oxides we can say strong bases, we can say. Next. In the crystal structures, if you see, this alkali metal monoxides coming under anti-fluoride structure. Anti-fluoride structure. This alkali metal monoxides coming under anti-fluoride structure. But cesium is exception. Cesium comes under which category in the sense? CdCl2 layer structure. CdCl2 layer structure. So lithium, Li, sodium, potassium, rubidium monoxide comes under anti-fluoride. Cesium comes under CdCl2 layer structure.